Welcome to Calculus. Today we will investigate using the mean value theorem to find a c-value in a given interval. We'll take a look at two examples. Our first example has a function that is a quadratic. It's y equals negative 2x squared minus 16x minus 32. And we're interested in this parabola from the interval from -5 to -3. Let's start off by graphing the function just so we have in view what it looks like, and then we'll state the mean value theorem. But let's create a table of values to plot this graph. And again, I'm only going to plot from -5 to -3. So in fact, just 3 points here. So we'll put X and Y. And for the outputs here, I'm going to just plug in these X values. So -2 times -5 squared minus 16 times -5 minus 32. And that all comes out to -2. If I plug in -4 to the same function, so again, -2 times -4 squared minus 16 times -4 minus 32. Total output there, because of some cancellations of signs, is going to be 0. And then lastly, if I plug in -3, I see that this is, again, -2. So we've caught the vertex of this quadratic within that small window of the domain. So I just want to graph it. So at -3, it's at -2. -2, it's right on the x-axis. And then at -1, it's back to -3. And here's our curve that we're considering when we look at the mean value theorem. So let's state the mean value theorem and just put that there so we can contextualize and say, what are we really looking for? So here's the mean value theorem. And it begins with two characteristics that I have to fulfill for the hypothesis or for the conclusion to be valid. So the two criteria are the same that we saw for the extreme value theorem. If, in fact, Rawls' theorem as well, if f of x is continuous on an interval from a to b, and that's a closed interval. So that's the first criteria. The function must be continuous on the interval. And so we can see from our graph that ours is continuous and differentiable on the open interval a to b. And so as I look at our graph, definitely the function that we've got is differentiable. There's no corners, no cusps. So if those two criteria are met, then the conclusion we can draw is this. Then C exists. So a number C that's between A and B such that we have this characteristic. The value of the derivative of the function at C will equal the slope of the secant line going through the endpoint. So f at B minus f at A over B minus A. And so let's say what this means in terms of our function that we're looking at. So we'll start kind of with that conclusion. We've already roughly verified that our function is both continuous and differentiable on the interval from -5 to -3. So we just need to think about the conclusion. So we are saying that there is some secant line that goes through the two endpoints left and right of the function. And what the mean value theorem guarantees that there's another x value between -5 and -3. And I see that I've graphed this wrong. Let me correct the graph real quickly. So -5, I had it shifted to the right, -4, -3. So the same shape, just got to get it translated to the right spot. So again, just to pick up with the mean value theorem. So if I consider that secant that goes through the two endpoints, there has to be another x value between -5 and -3 whose tangent line has the same slope as that secant line. And so we can kind of see that there is another, well, in fact, a tangent line that would pass through one point on the graph and be parallel to the secant line that's passing through the two endpoints. So that's essentially what mean value theorem is claiming. Now, for us, what we want to do is we want to find what is that specific C value. So the way that we want to do that is, first of all, just calculate what is this f at b minus f at a over b minus a. We want to calculate that out. So let's set that up. And the good news for us is that our table already has these values for us. We just have to fill them in to our slope formula. So f at b for us is going to be, we'll take this endpoint is our b, f of b. So we'll just plug that in. It's going to be -3 minus, so a and f at a is the other endpoint. So that's going to be -5. -3 minus -5, all divided by, and then I want to, okay, I'm mixing those up, guys. Let me make sure to get the correct order there. I was putting the x values in the numerator. Okay, we're squared away now. So let's catch that correctly. I got to put these -2 minus -2 over -3 minus -5. So that's a correct arrangement. So let's just calculate that out. Double negative will turn positive. So -2 plus 2 is 0. And we really don't need to check a lot in the denominator. That's -3 plus 5 is 2. So the slope we're interested in is 0. And we can kind of see that from our graph. So what we need to do now is find the C value that has the tangent line with a slope of 0. So to do that, I want to do similar to what we've done with Rawls' theorem and the extreme value theorem. I want to take the derivative of the function. So I'm going to take derivative, so y prime equals -4x minus 16, and then I want to set that equal to whatever slope we calculated in the previous step. So that happens to be 0. Place it there and let's solve. So I'm going to add 16 to both sides. And that gives me -4x equals 16. And then to finalize solution there, I'm going to divide both sides by -4. And that gives me the x value of -4. So what we're claiming here is that at -4, so we can locate that here on the plane, the function has a tangent line whose slope is 0, which matches the slope of the secant line going through the two endpoints left and right. So we kind of saw it on our graph roughly. The algebra that we've done here by finding the slope of the secant line and then taking the derivative, setting it equal to the slope of the secant line and solving confirms what we had seen on our graph. So this value here for C is -4, and I can see that that does occur between -5 and -3. So that example was a polynomial, and it showed confirmation of the mean value theorem with a 0 slope. Let's take a look at one that doesn't have a 0 slope and also is a radical function. So here I've got y equals -4x plus 4 all to the power of half. So that's a square root function. And I'm interested in that function on the interval from -3 to 1. Let's begin by graphing this like we had done with our parabola. So the domain's a little larger here, -3, -2, -1, 0, and 1. And we'll calculate, let me call that y instead of f of x. So again, I'm going to plug in -4 times -3 plus 4 to the power of half. That's all going to reduce down to 4. This on the inside would become 16. Square root of 16 is 4. We're going to have some irrational values because we are taking square root. So -4 times -2, that's 8, plus 4, that's square root of 12. So that's going to be irrational, 3.46 if we were to round to the thousandth. Also irrational at -1, so -4 times -1 plus 4, so that's 4 plus 4, 8. Square root of 8, again, is irrational. That has the value of about 2.83. Plug in 0, -4 times 0, that demolishes that term, plus 4 to the power of half, so the square root of 4 is 2. And then lastly, -4 times 1 plus 4, so that all becomes 0. -4 plus 4 is 0. Square root of 0 is 0. So we'll graph this function. At -3, it has the value of 4. At -2, it's at 3.46. So I have to estimate there. -1's 2.83. 0's at 2, and 1, sorry, is at 0. So here is our function. It's the right-hand side of a square root function that would continue over to the left into quadrant 2 if we were to extend our domain. But again, we're only dealing with the interval from -3 to 1. So there's my function. So again, I want to confirm the mean value theorem by first of all finding what is the slope of the secant line between the two endpoints. So I'm going to just sketch that in. Let me make sure it hits both of the endpoints. So what we need to do first of all is calculate the slope of that blue secant line. So let's do that first, and then we need to say where is the tangent line that has that same slope. So again, I've done all the work already in my table. Again, it's going to be f of b minus f of a over b minus a. So again, those come from the endpoints. So my f at b and b is 1, f at b is 0, a is -3, f at a is 4. So we need to calculate using those 4 values. So take the y values first. So 0 minus 4 divided by 1 minus -3. So that becomes -4 over +4, which is -1. So what I need to find now is what is the x value that has a tangent line with a slope of -1. So again, the strategy is now to take the derivative of the function. So we'll do that right now. So that's a square root function. I'll treat it like a polynomial, though I'm going to bring the half down as a coefficient. Do not change the composed function that's the base. And then half minus 1 is -half. And then using chain rule, I'm going to take the derivative of this -4x plus 4. That's just -4. So our derivative, I can combine half times -4 is -2 times -4x plus 4 to the power of -half. And in fact, what I'd like to do is let that drop to the denominator. And when it descends there, the power of half, negative half, becomes positive. And that I want to set equal to -1, the slope of the secant line. So I'm saying, where is the tangent line that has a slope that matches the slope of the secant that goes through the endpoints? That's really what we're checking with the mean value theorem. So I want to solve that now. So I see I can probably cancel this denominator by multiplying by itself in the numerator. So here on the left, that's going to cancel out, and that'll show up here on the right side. So then what I've got is -2 equals -1 times -4x plus 4 to the power of half. So then I want to cancel this -1. Different ways we could do that. I'll just divide by -1. So basically that will turn the 2 positive. So then I want to cancel the power of half by squaring both sides. So that'll cancel the power on the right-hand side, and it'll actually square the 2 on the left. So we get 4 equals -4x plus 4. So then that's just linear. We would subtract 4 from both sides. And at that point, the left-hand side is going to zero out to equal -4x. But even if I divide by -4, that won't change the 0. So what we're seeing here is the claim that this x value at 0 should have the same slope. Its tangent line should have the same slope as the secant line that goes through the endpoints. So I'm going to locate 0 on the graph. That's right on the y-axis there. And we're checking really the claim, is this tangent line have the same slope as the secant line? And graphically that checks out. So we can see it with our graph, but it's also supported by the algebra we've done by finding the slope of the secant line and then setting the derivative of the function equal to that slope and solving for the x value. Last thing we would want to check is 0 between -3 and 1? And absolutely, it is. So that confirms the mean value theorem. Well, thank you for joining for this investigation of the mean value theorem, looking at 2 different functions. See you soon.